video is going to be about a more detailed description on the toe clamp deal. I had a lot of questions on people asking about that. Looking at the tool changer here for a second, and I think I could answer the questions better with just a little video rather than trying to write in the comments, because it's a little hard to describe certain things in the comments. Also, bear in mind that I'm filming this in an actual shop, and I didn't realize it till I reviewed the video on the screenshot how much noise there was in the background. I tried to filter out most of that, but you can't get all of it, so kind of have to excuse the noise here. The machine is done here. I'm still finishing up the last one of these titanium plate things while I'm making this video. But there was enough questions, I think, to warrant a separate video on this subject. And I didn't want to add it to that titanium, facing the titanium plates down, because it just was getting too long, the video. And generally speaking, according to the analytics, people don't get to the end of the videos much anyway. So I thought this might be better for the people that had these questions. So let's look at a CAD model and see what my ideas were with this toe clamp. All right, there was some questions in the comments on the construction of this clamp, on various things on how it worked, and so I thought I'd do a video. I kind of promised to do a video on the last video on it, but there wasn't time. The video got kind of long, and so I thought I'd do a separate video here on it. So I've defined a plane here so I can cut a section through the clamp, so we can kind of look at what's going on here and why I did certain things here. It's going to kind of zoom in on the basic mechanism here. That this is just the screw that holds it down to the table. Well, there was comments on how this was so far back, and it is kind of far back in relation to the clamping end, I guess you'd say, of this thing, but it hasn't turned out to be a problem. When I tighten these down, I don't notice any lifting of the front end of this body of the clamp with the screw back that far, so it hasn't really been a problem, probably because of the angle, the low angle that this pushes forward at. And this is what I was thinking when I designed this thing. I wanted to, I kind of drew an angle here, and I tried to fit things in, and I started at about 20-degree angle with this, and it actually ended up being 17.5 degrees in the end. I had to be able to fit my wrench in here with the socket driver, an Allen driver in here, so that I could tighten it. And so that kind of dictated the size and everything of this, and the distance between here and the screw. This probably could be shortened a little bit. After looking at this model, I think I could have moved this pin forward and shortened the back end of this, and maybe shortened it another 5/8 of an inch or so, or maybe not that much, maybe about ½ an inch. If we measure the distance between here and the end of one of these serrations, it's about 5.446. So I probably could have shortened it up to, if I worked with these relationships, to maybe 5 inches long. This all could be scaled down. Actually, this is a pretty big clamp, and this is a big screw. This is a 5/8 11 screw and a 1/2 thread here, so this could all be scaled down quite a bit if a person wanted to. But there was questions on this, what I referred to in the video as a compound screw, but actually it's more accurately called a differential screw. If you search on the internet for differential screws, you'll see drawings that are similar to this. So the way this works is that we have a 5/8 11 thread here, which has about 90 thousandths lead per revolution, going into a 1/2 20 thread, which has 50 thousandths lead per revolution. So when you're threading this screw forward, it's losing 50 thousandths of its pitch because it's threading into this 1/2 inch thread, but it's still moving forward the difference, which is 40 thousandths of an inch. So that works out to, I think it worked out to a 25 pitch thread, equivalent of a 25 pitch thread threading forward, because 40 thousandths, 1 inch divided by 40 thousandths is 25. So that kind of gives a real nice feel and a lot of force available because it amplifies the force. These differential screws can be made in various different ways. Like if you had a left-hand thread here, then it would thread out faster per revolution than with the right-hand thread, because it would be adding to the lead actually. And if these leads were very close to each other in pitch, you could have a very fine movement, which I think they use this mechanism on like microscope focus adjustments and things like that. But I just wanted it so that I could actually have something that would push forward, and when you back this up, it actually pulls the jaw back as well. So you don't need any kind of like springs, or you don't need to be pushing the jaw back with your hand or something to get it to release. And it's got an 1/8 of an inch of movement because this slot here on this this is a 5/16 socket shoulder bolt here, and this is a 1/4 inch one back here, and there's an 1/8 of an inch of gap here in the slot. So I kind of designed this so that I knew this jaw was 1 inch thick, and I could mill this in here with a 1/4 inch end mill without too much difficulty to get that slot, and then I could just mill around this profile here, as you saw in the video, and that was pretty easy to do. And so that's kind of the way that screw works. I hope I've described that in a way that could be understood. I had to also make this nut separate. Originally I drew this up and I just put this thread in this moving jaw, but then I got to thinking about that after studying the model a little bit, and it wouldn't be able to be assembled. And even if I posted that on Instagram, Robin Renzetti even pointed that out to me, but I'd already kind of figured that out. But in a way that was most ideal, because that allowed me to make both the nuts out of bronze. Oh, that was another question. What were they made out of? And these are both made out of aluminum bronze on the steel set screw, and the steel set screw is kind of hardened a little bit. When I machined it, I could tell on the lathe it's a little bit hard, not real hard, but a little bit. And it has a very nice motion. You put a little grease on these threads and they have a very smooth motion to them. But it's necessary to have this rear pin here. This was another question. Why do you need that one? Well, the force of the screw, I intentionally wanted it to intersect the very top of this jaw over here. So if I drew a little model of a part here. So if we look at this, when it's pushing right here, it's going to want to pivot this jaw downward around. It's going to pivot around this 5/16 shoulder bolt, and that's going to do two things. It's going to put the thread in a bind. It's no longer going to be coaxial to this nut, if you will, the other nut in the moving jaw. And so I needed something to resist that rotation, and I put this 1/4 inch shoulder bolt back here, which is in essence just a pin, and it's riding along this ramped surface of the jaw back here. And that has all turned out to work really nice, actually. In actuality, when I use the clamps, the only change that I've added is this shield thing here. Let's go back to the full model. The shield on the top here, which would cover up this gap, because this gap opens up here when the jaw moves forward, and they can be at the maximum extension. It can be an 1/8 of an inch gap here, and shavings could get in there. So when you back the jaw, it might be difficult to back up. On the vertical position, I've been using them on the horizontal mill. This hasn't been an issue, but if these were laid down flat on a vertical milling machine, that would definitely cause problems eventually if the shavings were small enough to get in there. So this shield, I think, will more or less eliminate that problem. I just have to make that modification to my clamps. So I don't know if I've described that. If you have any questions about it on top of this, what I've shown, the only other issue is I had to be able to assemble this into the body of the um, of the actual body here, and that's the reason these slots and the nut is made here like this, so that I could actually put the moving jaw together with the nut, as you saw in the video, with the screw holding all that together, and drive roll pins down these holes, and then I could drop the whole thing into the base piece here and put these shoulder bolts through, and that would hold the whole thing together. That's kind of the reason it's made this way. And it does actually allow this bronze nut to slide up and down a little bit if necessary, although theoretically it shouldn't be necessary at all. But I haven't made things fit real tightly together here on purpose so that it would move nicely. So I hope that explains this better, because there was quite a few questions in the comments on certain things about this. But if you have more questions, just put it in the comments and I'll try to answer them.